Well, hello everyone. Welcome to the show. So, geometry. Yesterday we left off with some inductive reasoning. We did a little Tower of Hanoi. Today I've got another puzzle for you. What you're gonna do, excuse me. Hope your lunch was good. Mine was. We've got these little tiles right here. This little L shape, right? And your job is to tile a chessboard in such a way that it tiles the whole thing, covers the whole thing, except it leaves one square open. Doesn't matter where the square is. Okay? And your job is to figure out how to do that. As you can see with this example here on a 4x4 board, chessboard's 8x8. On a 4x4 board, you can lay down a piece like this and it covers up stuff, right? And you can potentially cover this up to cover up all but one hole. Obviously, a much easier question than this is a 2x2 board, right? You don't want to leave one hole open, you just put the piece there. You can also choose whatever hole you want. It's very easy to solve for that, right? If I wanted this hole open right here, I could just lay down my L shape here, right? So your job is to figure out how to do this for any hole. Doesn't matter which hole you leave. You just need to leave one. Again, if the problem's too hard, it's good to think of easier ones, which is why I put that up on the board. That's your challenge for today. I'm going to give you a little bit of time to do this. Cool. Alrighty. One way to write this down and turn it in is to, take a picture, obviously, and upload it to Google Classroom. That's one way to do it. You could also scan it. You could draw it in Paint if you want on your computer if you don't want to take a picture, or whatever easy app that you have for drawing or writing. You can potentially do it in Microsoft Word or in Google Sheets or Google Docs. Yes, so warm-ups do have to be turned in on Fridays, just like normal. Another way to do it is to write it out and go from there, right? Take a picture. So your problem was an 8x8. Anybody have any success in figuring out the 8x8? Is there a link? What is the warm-up? It's this. Ooh, hold on. That's too long. Warm up is what we're trying to do is we're trying to take a little L piece that looks like this. Like that. We're going to take as many as we need to cover up the entire board, but leave one space. The disc one yesterday, then you can go back and watch the video and grab it from there. The Tower of Hanoi. Alright, cool. And we'll be doing that one again soon. So you might be able to grab it then too. So your job is to take an 8x8 board, a chessboard, and place these pieces down such that you end up with this. Right? One square left over. Doesn't matter where the square is. We talked about how if you can't solve a tough problem, you might try easier ones, right? A 2x2 board's not too bad, right? 4x4 is a little tricky. 8x8's quite the beast. So Tower of Hanoi, Shelby, or this? Because we're talking about Tower of Hanoi, I would like to do that later. But if you're talking about this, the way you'd write that down is like this. So you might give it a couple goes. You might start placing pieces down, doing little L shapes like a line like this right here. Okay? But before I attempt this, yeah, you can rotate them. Yep. Before I attempt this, I'm going to attempt an easier problem, right? So for instance, 2x2s. So if I wanted to do this, and I wanted to leave this square open, very simple, I just put my piece like that, right? If I wanted to leave this square open, I just put my piece like this. And if I wanted to leave this square open, I'd put my piece like this. And if I wanted to leave this square open, I put my piece like that. So I've actually found every single possible way to win the 2x2 game, right? Right there. Those are the 4 possible ways to win a 2x2. Now, the 4x4, less challenging than the 8x8, still is quite the challenge. However, if you understand the simplicity here, you can actually apply this to the harder problem. And that's what we're doing with inductive reasoning, guys. We're taking a very basic case, and then we're showing that, look, if you know how to do this, you can do this for free. And I think a lot of you guys aren't seeing it quite yet. But if you know how to do this, which I think everybody is going to understand that, you win the next one up for free. This is a 2x2, this is a 4x4. So we're going to call this case K. Case K, very simple, we got it, right? This is case K plus 1. And if you want to go into the math for that, K is really like 2, right? To the first by 2 to the first. It's a 2x2 square, right? And this is going to be 2 to the second by 2 to the second. So 2 to the K is what this is right here, right? And this is 2 to the K plus 1. It's the next case. So our first case is when K is 1, right? 2 to the first. Our second case, the much more difficult problem, right, is when we have 2 to the K plus 1. Well, if K was 1 earlier and we add 1 more to it, right, we get 2, so 2 squared. So it's a 2 square by 2 square board, a 4 by 4 board, okay? Now I'm going to show that if you understand these, the base case, then the next case up, you get for free. Absolutely for free. So check it out. This 4 by 4 board is actually just 4 2x2 boards. You see it? This right here is just this little part right there. So the next case up is just 4 of these guys. So instead of trying to place L's on here, what I'm going to do is I'm going to take these guys and place them on here. However I want. So I might take this first one here, and I might place it up here like, I don't know. How about, let's place it down here actually. Let's place it like this. So I just moved that guy to here. And see how it left 1 square left over? Right? Now, we still have plenty of other squares left, but we're going to use these tiles here, what we found out before, to kind of get this board solved for free. I'm going to take this one. I'm going to put it there. Again, leaving 1 square left over, right? I'll take this one. I'll put it here. And then I'll take this one and I'll put it here. And you'll notice that I left 1 square left over for each of these, right? That makes sense. 1 there, 1 here, 1 here, right? And 1 square here. And that leaves us with 4 squares in the middle. And now, if you're clever, you'll see that what is left over, those 4 squares that are left over, well, they form another 2x2 board. And we know how to solve a 2x2, right? We know how to solve a 2x2 board, right? So what we're going to do is take one of these pieces, doesn't matter what it is, and we'll place it here, maybe. So we've covered all our squares except 1. So if you can see that the more complex problem is just a bigger version of the simple problem, it becomes very easy to solve. I made it so there's 1 square left over here, and then that left over one of these guys. So I could easily solve it. So what you have to do is you have to show that the bigger problem, after you do some work, is really just a bigger version of the simpler problem. And you know how to solve the simple one, right? So we win. There's one way to do it. Now, if I wanted a different square to be left open, not just this guy, right? Because we showed every way here. I'm not going to show every way. There's too many. We're going to use inductive reasoning to prove that this would work. I left 1 square open here. What if I wanted to leave this square open, right? Well, then I would just rotate my L and put it down differently. So, for instance, I would do this, right? 1 here, 1 there, 1 here, and 1 there. And then if I wanted this square open, well, then I put my piece here. If I wanted this square open, then I put my piece here. If I wanted this square open, I put my piece there, right? I can choose any square that I want. In fact, I can even choose an outside square if I want, because what I can do is I can do this. Let's say I wanted this square left over. Well, then I do the same as I did before, right? And I'd leave that square open. So what I'm going to do is I'm going to look at that, right? I'm going to put my piece here. Right? And then I'll drop my last piece in here. So again, what I did was I put a piece here, a piece here, and a piece here. And then I turned this piece to leave this square open, and then filled in the rest here. So for any square that I want, I can just adapt my strategy to leave that one open. But the strategy is simple. The strategy breaks down to make this problem an easier problem, right? Send it back to one of these. So how does that apply to the 8x8? Well, an 8x8 is just the next case. If we make this the base case, right, the 4x4, the next up is going to be an 8x8 because we have a board that is 2 to the third by 2 to the third. So we went from 2 squared, 4, by 2 squared, 4, 4x4, right, to 2 cubed by 2 cubed, 8x8. So it should be the same problem. It's the next case. It's the next one in the line, k plus 1, right? So what we're going to do is we're going to break this board down into 4 4x4s. Cool. And we know how to solve 4x4s. This time, what I'm going to do is when I do 4x4s, I'm going to leave these spaces open here. I'm going to leave those spaces open. So what I end up with is a smaller 4x4 in the middle. So what I want to do is I want to leave this open in the middle. Because if I can clear out all of this stuff, right? If I can get rid of all of that, then I'm back to a 4x4, which I know how to solve. I know how to solve a 4x4, right? So I need to get rid of all these guys. And that's not very hard to do. I want to get rid of all these except this 4 right here. So what I want to do is take care of the rest of this here first. So I'm just going to focus on this little corner down here. Okay. And I know how to solve something like this because I know I just need to leave this piece left in the middle, this piece right here. So here's how I'm going to solve it. I'm going to get rid of this, I'm going to get rid of this, and I'm going to get rid of this. And now I've got this part left over, right? I want to leave this, so I'll put my last piece here. And now I have that left over. I'm going to do the same thing over here. I'm going to leave this middle part, right? So I go around it. Here, here, and here. And then when I have this middle part, I do this. And now all that's left is that. I'm going to do the same thing here. I want to leave this middle part in a 4x4, right? This is a 4x4, so I'm going to get rid of everything except this right here. So to do that, I do this. And then I'll do this. Again, leaving this left over. Same thing over here. I'm first going to focus on it as a 4x4. And I'm going to leave the middle. I know how to do that. Right? And I'd put another one here if I wanted to leave the middle. But now I want to leave this part. So I'll just put my last piece here. And now, as you can see, I've got everything covered up except this middle part. And what is this middle part? It's a 4x4. Okay, well, I can solve a 4x4. You tell me what square you want me to leave over or leave left behind, and I will. You want to leave the square in the middle? Awesome. There we go. Now I'm down to a 2x2. You want a square in the middle? This square? Awesome. Then I'll put my piece here. Works every time, no matter what, no matter how big the board gets. You can imagine that if I made this a 16x16, right? It would just be 4 of these big squares, right? This whole thing. And I'd go about solving it the exact same way. I'd whittle it down to an 8x8 in the middle. Then I'd whittle it down to a 4x4, then a 2x2, and then I'd solve. I'd leave my last square. So the idea is that if you can solve the trivial case, right? Boring, right? And show that the bigger problems are also just bigger versions of this, right? Then you get the next one for free. And if you can do this one, then you get this one for free. And if you can do this one, then you get the 64 by 64 for free. So we showed that the 2 to the first board by 2 to the first, this board, right? We showed that 2 to the first by 2 to the first, that board, very easy, trivial, right? Done. I can get you any square you want left over. Which then we showed that the 2 to the second by 2 to the second board was just a bigger version of this. It was a board that had this built into it. Right? And then what was left over was this middle part. And then we solved, right? And so on and so forth. That then got us the 2 by 3 by 2 by 3 because this right here is just going to be contained inside this guy. So the 2 to the third by 2 to the third board is just a bigger version of this, and this is just a bigger version of that. So inductive reasoning allows us to conclude that this is possible for any version of this board. A 2 to the 1 by 2 to the 1, a 2 to the second, 2 to the second, a 2 to the third, 2 to the third, a 2 to the fifth by 2 to the fifth, right? You could all go all the way up to a 256 by 256 board, and it would just be the same process. And you can get any square you want. Now, through normal deduction, we are not able to check every single possible board, right? There's infinitely many of them. But through induction, we're able to say, look, if I can get the first two, it proves the last one. Because the easy case, right? The easy case is contained within the harder version. It's just 4 of those easy ones. If you can solve one easy one, I bet you could solve 4 easy ones, right? That's the idea. If you get the base case, it knocks over the first domino and knocks over all the rest. So there's 2 things you need to show that the dominoes fall down. 1, that the first domino does fall, right? That it's easy. We can do the first one, right? And 2, that the second domino, the next problem, is just a harder version of that. And if you understand that, you get that for free, right? So that if you get the first one, the second one does fall. And if the second one falls, well, pretend that's the first one now. Since it fell, the third one should fall. Okay, the third one fell, pretend that's the first one. If it fell, the next one should fall, right? It gets all of them in a row. So all we have to do is show that it works for the first case, and then it works for the next case after that. For any case that it works for the next one after that. So as soon as we knock one case down, it knocks down all the rest. That's the idea, okay? And I'm going to send you guys a video that I kind of stole this problem from. Great visual example. I'll send you this video a little bit later. It's got some stuff in it I want to use for my lessons later. And I think it'll help you guys be able to see what's going on here a little bit better if you're still confused. But that is the idea of inductive reasoning. That if you get one thing, then it proves the next. And this is super useful for things that are infinite, because if it's infinite, you can't just check every one, right? But you can check the first one and the next one. And then through inductive reasoning, it means all the rest must be that way. So we got to prove that the first one falls down, and that after the first one falls down, the next one is just a bigger version of the first. It's the same thing when you boil it all down. Okay? So yesterday what we attempted to do, was take this infinite series, okay, and add it all up. So we said we're going to sum the natural numbers. That's what that symbol means. Big N. Dang, she thick. So here's the natural numbers all added up. As high as you want to go. Okay? Pick up to 50, pick up to 100, pick up to 1,000, whatever you want to go up to. Or just, stop at 1, or stop at 2, or stop at 3, right? Whatever you want to do. It will equal the number you chose to stop at times the number after that number, right? See how n plus 1 stands for that? If we stop at 4, then we're going to times that by the next number, 5, right? N plus 1. All over 2. Now, what we're learning today, like I mentioned yesterday, doesn't help you come up with this formula, right? Because you're like, how is that? But it does let you prove that it is. To come up with a formula, you need algebra, and you need to learn what we're learning in the next week or two with my algebra class right now. So if you're interested in how to come up with these formulas and these really interesting strategies of how to solve a complex problem, right? Tune into my algebra class or watch it later, because it starts at 10. I think most of you guys are sleeping in. But if you want to prove that it works infinitely, right, for any number that you want, you need what we're doing in geometry, okay? So if you had algebra with me last year, you'd be able to come up with this answer. And then now we're going to prove that that has to be the answer. And the way we're going to do that is inductive reasoning, right? We can't check it for every number. We can't check it up to 1, up to 2, up to 3, up to 4, up to 5, right? We have to check it for the first couple and then use inductive reasoning to prove that it will work for the rest, okay? So here's what we're going to do. Our first job, if you remember from yesterday, is we're going to prove the base case, right? The first case. We're going to prove that it's easy to solve the basic problem, right? That it works. And that's very easy to show. We can show that. We can show an example. So let's prove when n equals 1. Okay? So we're going to prove when n equals 1. Well, when n equals 1, we stop after 1, right? So all that's gone. It's just the first number. And that should equal n times n plus 1 over 2. And remember, what does this mean? Don't get confused by all the algebra. N times n plus 1 over 2, right? That's bizarre, right? It's weird. It means a bunch of mumbo jumbo. What it means is the number you chose times the number after that, right? So when you add 1 to a number, you get the next number. So the number we chose was 1. And we're going to times it by the number after that, 1 plus 1, which is 2, right? See how it gets us the next number? Well, that equals 2 over 2. Which does equal 1. So yep, we proved it for the first case. Both sides match, we win. Okay, so the first domino has fallen. Okay? We're going to assume that no matter which domino you push down first, we chose the first case, right? Well, we could have chose the third case or the fourth case or whatever. We're going to assume that no matter which one you knock down first, that it'll work, that you'll be able to knock it down. So if I chose to stop after 4, it would work. And again, we can show this, right? 1 plus 2 plus 3 plus 4, that's going to be 10. 4 times 5 is 20, divided by 2 is 10, right? So we're going to assume that no matter which one you choose first, right? We chose 1, but no matter which one you choose, then it would work, okay? So we're going to assume n equals k is true. Okay, we're going to assume that no matter which case you individually choose to test, right, that it will work, that you will get the right answer using this formula, okay? So if any case that we choose to knock down first is true, now we just need to prove that the one after that case will also get knocked down. That one after it will also be easy to solve, okay? And so what we're going to do is show algebraically that that is true. So now our job is going to be to prove this. We want to prove that n equals k plus 1 is true, so that the next number will fall. In other words, we want to prove this. Here's when n equals k, right? Here's the formula. 1 plus 2 plus 3 plus all the way up to n, which we switched out for k, right? Equals k times k plus 1 over 2. So whatever number you start or choose to stop at, right here, that it will work. We're assuming that that's true. What we want to prove is that the next number after this number would work. So if you wanted to stop at 7, right, you'd write 1, 2, 3, 4, 5, 6, 7, right? And then you plug in 7 and 8 here and you do your math, right? We want to prove that it works up to 7 and the number after that. So we're going to prove this, okay? So this was the assumption, right? Here's what we're trying to prove. That 1 plus 2 plus 3 plus k plus the next number after k. Well, how do I write the next number after k? I don't know what k is, right? Well, to write the next number after k, I'm going to write k plus 1. Do you see how that works? If your number was 7 for k, then the next number after that would be 7 plus 1, 8. If your number was 100 for k, right, you went all the way up to 100, then your next number would be 100 plus 1, 101. So we're going to show that it works for all the way up to k plus 1. The number you chose, right, which we know works because we assumed it. And then we're going to show that it works for the next number, okay? So instead of k, right? I'm now stopping at k plus 1. So I'm going to write k plus 1. And instead of k plus 1 here, since I'm stopping at k plus 1 already, I need the number after k plus 1. What's the number after k plus 1? Chat, let's see how far you guys are behind. What's the number after k plus 1? Here's k. Here's k plus 1. K plus 2 would be the next number, right? K plus 2. N we're leaving in the past, Haley. Forget about N. We're talking about specific cases, so we use the word K. I know it's kind of weird, like, why did we switch from N to K? Okay, it's all right, it's all right. This is weird. It is. It's not hard once you see it. You're like, oh, okay, K plus 2, right? But it's weird. So don't be afraid of being wrong. So instead of writing K times K plus 1, I'm going to do K plus 1 times the next number, K plus 2. Still all over 2, right? And if I can prove both sides are the same, I win, like we did up here. See how we proved both sides were the same? Then we win. So the question is, how do I get this to look like that? Now, the trick is for all of these inductive reasonings. Hi, Anna. The trick is for all of these inductive reasonings, you're going to want to turn part of this, okay, into what we assume to be true. So here's what I mean. We assume this, right? This was our assumption. That if we go up to a certain number k, that it works. Okay? Well, notice that this right here is the first half of that, right? It's the left side. We assume that this equals this, right? So we're allowed to use it. So I'm going to write, instead of this, I'm going to change that into this, the thing we assumed, okay? And that's going to help us make it look the same on both sides. So first thing was we assume n equals k, and then we prove the next one up, right? So we assumed when it equals k, when we stop at k, that it works, right? Then we're going to show that when we go one higher, that it also works. So it works for the first one, it works for the second one, right? It should make all the ones fall, and then we win, right? So this right here, we can rewrite as this. Right? See how 1 plus 2 plus 3 plus all the way up to k equals this? Well, that's what I have here. 1 plus 2 plus 3 all the way up to k, right? Ignore this. And it should equal this guy. So I'm going to rewrite that as k plus 1 over 2. I'm just doing a substitution, right? So by substitution, I'm doing this. I don't need you to write that. We're just doing algebra, okay? And then I have this guy, right? Which I don't need parentheses for, but I'm just showing you it's one idea, right? It's the next number after k. Just using organizational parentheses here. So our job now is to show that both these are actually the same, that it does work for k plus 1. Okay? So I'm going to scoot this up. I'm actually going to pause for station identification if you're writing this stuff down. I would encourage you not to. I would encourage you just to watch. If you want to write stuff down, you can kind of fast forward the video later. I'm going to give you just a second to write this down and catch up. Ask questions to each other in chat. I'm going to use the restroom really quickly, and then I'll be back, okay? Just want to give you a little pause of station identification. Sorry it took so long. I had to sing happy birthday twice while washing my hands. It's the right thing to do. Right, yeah. So this formula, again, how did we come up with that formula? Magic. Algebra, really, okay? I just came up with it for you. So if I were to give you this problem, I said, prove this, I would not say, what does that equal? I wouldn't do that. I do it to my algebra kids. I wouldn't do it to you guys. I would say, assume, prove this true, right? Kind of like I do with other geometry stuff, right? Prove those lines parallel. I wouldn't say prove it, and you'd be like, wait, what? Prove what? And I'd be like, well, prove it, prove the thing, right? Prove something about this. No, I would be like, hey, prove that this is this, okay? And what does this formula say? I want you to think in terms of what the formula means, not what it actually like is. Everybody, like it's n times the quantity of n plus 1 over 2, right? What does that mean? What does it mean? It means the number you stopped at times the next number divided by 2. Always gets you the thing. So for instance, if I stopped at 7, 1 plus 2 plus 3 plus 4 plus 6, 7, right? If I add those all up, that'll be equal to 7 times 8 divided by 2. 56 divided by 2. Okay. So here, I went up to k plus 1. So k plus 1, and then the next number, k plus 2. When you multiply those together and divide by 2, it should equal this. We're going to prove that that's true, okay? And the way we're going to do that is we're going to make both of these sides look the same. This right here goes up to k, and we know that equals this, right? We assume that. So now what we're going to do is I'm going to rewrite this on a separate sheet of paper so we don't have that issue we had yesterday. K times k plus 1 over 2 plus k plus 1 equals k plus 1, k plus 2 over 2. And again, what does this mean? It's saying all the numbers up to k added together plus the next number, right, will equal the number we stopped at, right, k plus 1, times the next number after that divided by 2. So let's prove that these are the same. Now we need to do algebra to make this happen, okay? Let's talk about algebra. I think some of you guys got lost in the algebra yesterday. So let's talk about algebra. Let's take a little bit of a break from what we were doing. How would you solve a problem like Maria? Ooh, we need that as a sound that you guys can play. That's what we need. Do we have to write this? You don't have to write anything. Distribution. Thank you, Lainey. We know if it was just a 2 and an x there, you'd multiply them, right? But because we have two terms here, do you see I have an x and a 1 there? Remember we talked about terms, right, separated by a plus or a minus? The 2 doesn't just multiply to the x, it also multiplies to the 1, right? Because this is 2 times all of this. That's what that parentheses means. So it goes to the x and goes to the 1, everything inside the parentheses. So 2 times x is 2x, and 2 times 1 is 2. Cool. It doubles the whole thing. If you have an x plus 1 and I have an x plus 1, right, we have twice. We have x plus 1 times 2, right? We've got 2 x plus 1s. Okay? In other words, we have 2x plus 2. Okay? So you know how to solve that. What about something like this? Well, some of you might say, well, I know 2 plus 5 is 7, and then I distribute it. 7x plus 7, right? And that checks out, right? This is 7. And then we distribute it. FOIL is great. First, outer, inner, last. Exactly, right? That's one way to do it. Now, the problem with FOIL is that imagine I had more than just 2 guys here and here. Then there's no first, outer, inner, last. So like if I had... right? Your first, outer, inner, last doesn't work. All it is, guys, is distribution. So it's 7 and we distribute, right? No big deal. But what if we weren't able to combine the two? What if we aren't able to combine these two, right? If we are, then it's 7 and we distribute, right? No big deal. It's the same problem as this, just with the 7. But what if we have this? Right? First, outer, inner, last, sure, because there's 2 on each, right? If there were more, you'd be in trouble, and I can show you that in a second. It's distribution. If there was just a 5 here, you'd know what to do, right? You would distribute the 5. And what would you get? You get 5x plus 5, right? No big deal. What if there was just an x here? Well, you'd know what to do, right? You distribute the x. If there was just an x here, you do x times x and x times 1, right? And you get x times x, which is x squared, and x times 1, which is 1x. And then to make your math teacher happy, you'd put all this together, right? You combine like terms. X squared has no body to go with. X and 5x go together. It's a lot of x's. Again, terrible idea in real life, great idea in math. Get your x's together. Cool. And there'd be your answer. That's as simple as it can get. Now, the reason FOIL, I don't like to teach FOIL, is because it makes it seem like it's not distribution, like it's some special trick that you have to do, right? And it's not. It's just distribution. Also, when you get to higher level math, you're going to have more things. So pretend we had this. Right? Ugh. Where are your gods now? Where are your gods now? There are no outers, inners, and lasts, right? Distribution is all we're doing here, guys. That's all it is. I would distribute the 1, right? If there was just a 1 here. So let's do that. Right? If there was just a 2 here, 2x here, what would you do? Well, you distribute the 2x, right? We get 2x squared. 2x times x is 2x squared. And 2x times negative 5 is negative 10x. Well, what if there was just an x squared here? What would you do? You distribute the x squared. You get x squared times x, which is x cubed, and x squared times minus 5, which is minus 5x squared. That's a positive x here. Right. And then you combine them all up, blah, 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 right? We have an x cubed here. He has no body. We've got 2x squareds, minus 5x squared, and positive 2x squared. That's negative 3x squared altogether, right? You had 2x's, and then you subtracted 5. You're down to negative 3x's. For our regular x's, we have an x minus 10x. That's 9x negative, right? And then we just have a regular minus 5. Ta-da, we win, right? So check it out, guys. It's just distribution. It doesn't matter how many things you have. You don't need to think, okay, the firsts go together and the outers go together and the inners go together. Too complex. You don't need that. Just do math. Just distribute. That's all you gotta do. No matter how big it is. And again, it's gonna get complicated the bigger it is, right? I feel like there's an opportunity there for you guys. I feel like you should utilize that. Although it might be on delay. When it gets bigger, it gets more complicated. But it doesn't mean it's harder.
That's what she said.
We need to get you guys off delay. Your game's slipping. Your game's slipping. So, back to the actual problem. And look, if you are behind, don't show up to the party late, okay? Don't come late. I already did it. Here we go. So we're here. We're going to make this side look like this side. Well, I can distribute this, right? This isn't too bad. K times k is k squared. And k times 2 is 2k. 15, 20, 21. Then we have 1 times k, which is just 1k. And 1 times 2, which is 2. Y'all over 2. Okay. On this side, we can distribute the top here. So we're going to get k times k here. It's going to be k squared. And then k times 1, which is k. Right? So far, so good. Now notice how all of this is over 2. We can simplify the top part. K squared, 3k's, plus 2. This is not all over 2, right? We have this little thing that's sticking out, right? We need to make sure that's over 2 as well. So, how do I make this guy over 2? Let's talk about algebra. Kami denomies. These two fractions have a common denominator of 2. They're both over 2, which means we can combine them by addition or subtraction, in this case subtraction, to be over 2 for one answer. And it's very simple. If they're all over 2, then you just subtract them like normal. 3 halves minus 1 half. If I have 3 halves and I take away 1 half, how many halves do I have left? We'll pause for station identification. If I've got 3 halves and I subtract 1 half, how many halves do I have left? 2 halves, right? So problem solved. Super easy. Boring. And it's because they have common denominators. If I don't have common denominators, right? I don't have common denominators. This guy's over 2, that guy's over 4. I need to make them common. And the way we make them common, notice that this right here, I want to know what it equals, but I don't have an equal sign. I can't multiply both sides. I can't do anything like that, right? What I have to do is work with what I got, okay? So what I'm going to do is I want that 2 to be a 4, right? If that was a 4 down here, then they'd be common and we would win. So here's what I'm going to do. I'm going to multiply this fraction, just this number right here, okay? I'm going to multiply the bottom by 2 to make it a 4, okay? We can't add or subtract, right? Because then we'd have to do it to both sides. I'm going to multiply the bottom by 2 to make it a 4. Cool. Now it's a 4. But if I wrote a 3 up here, that'd be 3/4 minus 2/4. 3/4 minus 2/4 was not the original problem, right? So I changed the problem. That's not allowed. But luckily, I can multiply the top by 2 as well. And that'll make it a 6. Now, why did that not change the problem? Well, first of all, 6/4 does reduce to 3 halves. They're the same number, just a different way of looking at it. But the reason it didn't change the problem is because when you multiply by 2 in the bottom and 2 in the top, what you're really doing is multiplying by 2 divided by 2. And what is 2 divided by 2? What is 2 divided by 2? What is 2 divided by 2? It's 1! And multiplying by 1 doesn't change anything, but it can make it look different. But it's the same thing, right? 6/4 does reduce to 3/2. It's the same number, it's just a different way of looking at it. It's a change in perspective, and that's what algebra is all about. We can't change the problem, but we can look at it in a different way, which is always what we should be doing, right? This goes back even to our game that we were playing earlier, right? Looking at this is just 4 of those put together, right? So we do the problem. 6/4 minus 2/4, all quarters, right? 4/4. Checks out. Now, what if we have a problem where one has a denominator and the other doesn't? Well, 2 ways of doing this. You can think, well, there really is a denominator there. I'll multiply by 2 in the top and 2 in the bottom on this side, and I'll get 10 halves. And notice 10 halves is 5, right? 10 divided by 2 is 5, so we didn't change the problem. And I'll find out that it's negative 7 halves, right? Another way of thinking is saying, how many halves are in 5? Right? 10 halves are in 5, and you can check that by saying 10 divided by 2, yep, it's 5. I didn't change the problem. It's the same question, it's just a different way of asking it. 3 halves minus 5, you can ask that question again, but in a different way, by saying 3 halves minus 10 halves. Same idea. Okay? So now back to what we were actually looking at. The K's. So we want these to be common, right? One's over 2 and the other isn't over anything. Well, technically, it's over 1, right? It's over 1. And we want that 1 to be a 2. So we have to multiply the bottom and the top by 2, right? Multiplying by 1 doesn't change the problem, just makes it look different. And what we get is k squared plus k over 2 plus 2 in the bottom here, right? 2 times 1. And then 2 times k plus 1. Now, be careful. This is not just times one of them by 2. It's times all of this by 2, right? We're timesing the whole top by 2. So it's going to be 2k, 20, plus 2. Okay? We distributed that 2. Because it's times all of the top. We're doubling the top. K plus 1 is 1, right? 1 piece. If we double it, now we have 2k plus 2. Now, notice they're all over 2 now. So I can write them as just one fraction. How do I do that? Well, if they're all over 2, I write a 2 in the bottom, and then I just add up the top, right? That's what we do. We're combining them. So I have k squared. I have a k here and 2 k's there. That's 3k. And notice that's what I have on this side, isn't it? They're the same. So I got common denominator, so it would look like this, right? And it turns out it's exactly like that. So what we've just proven is that it does work for k plus 1. So we said, if you can find a case where it's true, right? If you can find a number that when you do the math, it works out, then the one after that should also work. We proved that the one after it also should work. Now, we assumed that there should be a number that will work when you do the math, right? But here's the thing. Remember earlier? We did show that there's a number that works. We showed that 1 works, right, when you do the math. And then we showed that if you can find a case that works, right, then you should be able to find that the next case after that will also work. And we proved that that does, right? That if you do k plus 1, it does end up working, right? It's the same. So if you can find a case that works, then the next case after that should be true. Well, here's the thing. We know a case that works. 1 works. So we just proved the next case after that works. So 2 works. Well, wait a minute. If 2 works, then we know that there's another case that's true. And the one after that should work as well, right? So 3 should work. Well, if I know 3 works, right, then I know that 4 should work because this is true. Well, if I know that 4 works, then I know that 5 works, right? Et cetera, on to infinity. So I know for any case, for k greater than 1, it works. Or equal to, I should say. So if k is 1, if k is the number we're going to try, 1, right? Then we know it works. Well, then we know the next one after that works. Anything greater than that, right? Everyone after that will fall. So this is a very powerful method, right? We assume that if we can find 1 case, then the one after that also we get for free. So we prove that the one after does work, right? And then we show that, look, there is 1 case where it works. So everyone after 1 will work. So stopping at 1 will work. Stopping at 2 will work. Stopping at 3 will work. Stopping at 4 will work. They'll all equal this, no matter where you stop. And through this powerful method, we're able to prove something that goes on infinitely. It could stop at any point, right? But we know it has to work. Because if it works for 1, it works for the next one. If it works for 2, it'll work for the next one after that, 3. If it works for 3, it'll work for 4, and so on and so forth. That is inductive reasoning. We did it with this. We showed that it works for the first case, right? And we showed that it would work for the case after that. Because it's just this guy with a little bit extra, right? So anyone that works, we know the next one will work. Because this guy is just contained in here, right? The bigger version. So if 1 domino falls, they all fall. So again, what do you have to do for inductive reasoning? Prove that it works for 1 case. Okay? And assume that if you do have a case that's true, which we do secretly in our back pocket, right? Then that the one after that also works. You have to do math to make them look the same, right? And then, if the one after a case that is true works, and we have a case that's true, then we get every case after the case we knew before. So if we know 1 is true, then we get 1 plus 1 to be true, the second case. If 2 is then true, then we get the one after that, 3, right? And so on and so forth.